Albert Einstein's special theory of relativity famously dictates that no known object can travel faster than the speed of light in vacuum, which is 299,792 kilometers per second. This speed limit makes it unlikely that humans will ever be able to send spacecraft to explore beyond our local area of the Milky Way. However, new study from the University of Göttingen's ERIK LENTZ reveals that there may be a method to get beyond this barrier. The catch is that his plan demands a tremendous amount of energy and may not be capable of propelling a spacecraft. Traditional energy sources, according to LENTZ, may be capable of creating the structure of spacetime in the form of a soliton, a powerful solitary wave. This soliton would function as a warp bubble, compressing space in front of it while expanding space behind it. Spacetime, unlike anything within it, can bend, expand, or warp at any speed. As a result, a spacecraft trapped in a hyper-fast bubble may travel faster than light in normal space without violating any physical constraints, including Einstein's cosmic speed limit. The concept of manufacturing warp bubbles isn't new. It was first presented in 1994 by Mexican scientist Miguel Alcubierre, who dubbed them warp drives in reference to the Star Trek sci-fi series. Until Lentz's findings, it was considered that the only method to make a warp drive was to generate massive amounts of negative energy, potentially through the use of undiscovered exotic matter or dark energy manipulation. To solve this challenge, Lentz devised a previously unknown geometric structure of spacetime from which he derived a novel family of solutions to Einstein's general relativity equations known as positive energy solitons. Though Lentz's solitons appear to comply to Einstein's general theory of relativity and eliminate the necessity for negative energy, space agencies are unlikely to build warp drives in the near future, if at all. Lentz's positive energy warp engine necessitates a large quantity of energy, which is one of the reasons. According to Lentz, a spacecraft with a radius of 100 meters would require energy equivalent to hundreds of times the mass of Jupiter. He goes on to say that for this demand to be realistic, it would have to be reduced by around 30 orders of magnitude to match the output of a modern nuclear fission reactor. Lentz is looking into existing energy-saving techniques to determine if the amount of energy needed may be decreased to a manageable level. Any warp drive would also have to deal with a slew of other difficulties. The horizon problem is one of the most harmful, according to Alcubierre, who considers Lentz's work to be a major development. A warp bubble traveling faster than light cannot be generated from within the bubble, he argues, since the leading edge of the bubble would be beyond the grasp of a starship sitting in its center. The issue is that you need energy to bend space all the way to the bubble's very edge, which the spacecraft simply cannot provide. Another recent study on the problem is presented in an accepted publication from Advanced Propulsion Laboratory researchers Alexei Bobrik and Gianni Martire, who discuss their calculations in classical and quantum gravity. The duo offers a generic model for a warp drive that incorporates all extant positive energy and negative energy warp drive schemes, except Lentz's, which likely forms a new class of warp drive spacetimes, according to the couple. They contend, however, that a Lentz-type warp drive is similar to other warp drives in that it is a shell of regular material at its core, and hence subject to Einstein's cosmic speed limit, concluding that there is no known technique of speeding a warp drive beyond the speed of light. Although he knows the enormous challenges of developing a warp drive, Lentz believes they are not insurmountable. This effort has taken the problem of faster-than-light travel one step closer to engineering from theoretical studies in fundamental physics, he says. After addressing energy needs, Lentz wants to design a method of producing and accelerating, and dissipating, and decelerating positive energy solitons from their constituent matter sources, then confirm the existence of small and slow solitons in the lab, and finally address the horizon problem. Passing the speed of light with a completely autonomous soliton will require this, he argues. We hope you liked the video. Like and share the video if you learned something new. Subscribe to Explified so that we can keep you updated on the hot and happening in space. See you in the next one.